Today, we are diving into one of the most profound technological shifts of our time, quantum computing. And to really get it, you're going to have to forget just about everything you think you know about how computers actually work.
So let's just start with the big one, the question that really sets the stage. How in the world can a computer solve problems that would take our fastest supercomputers literally billions of years to crack? The answer? Well, it's wonderfully strange. They do it by playing with a completely different rulebook. See, quantum computers don't just work faster, they work in a fundamentally different way, tapping into the bizarre and, frankly, awesome laws of quantum mechanics itself. Okay, so let's get into it. Before we can understand where this is all going, we first have to understand the limits of where we are right now. And that limit, it's the simple, reliable, but pretty restrictive world of binary code.
Every single computer you've ever used runs on bits. And a bit is like a light switch. It's either on or it's off, a 1 or a 0. It's simple. A quantum bit, or qubit, well, that's more like a spinning coin. While it's spinning, it's not heads, it's not tails. It's kind of in a state of both possibilities at the exact same time.
And that whole spinning coin idea? Well, that leads us right into the first quantum superpower. This is where reality starts to get a little flexible.
It's a principle called superposition, and it's the core idea that a qubit isn't forced to be just a 0 or just a 1. No, it can hang out in this beautiful, blended mix of both states simultaneously. It only chooses a side when we actually measure it. And here's where your brain might start to hurt, but in a good way. This power grows exponentially. 1 qubit holds 2 values, right? 2 qubits can hold 4, 3 can hold 8. A few hundred perfectly stable qubits could hold more values than there are atoms in the entire known universe. Just let that sink in for a second. That massive information space is the engine for its incredible processing power.
Now, if existing in 2 states at once wasn't strange enough for you, let's add another layer of weirdness. Let's talk about the second quantum superpower.
This one is called entanglement. It's this special, almost magical connection where 2 or more qubits become linked, and their fates are totally intertwined. Whatever happens to one instantly, and I mean instantly, affects the other, no matter how far apart they are.
It's a connection that literally doesn't care about space. This is the thing that famously baffled even Albert Einstein. He's the one who called it spooky action at a distance. Imagine you have one of these particles, and its partner is on the other side of the galaxy. The second you observe yours, you instantly know the state of the other one. Let me break it down. First, you link 2 qubits together. Then, you can separate them by any distance you want. Across the room, across the solar system, it doesn't matter. The moment you measure one of them, forcing it to pick a state, its partner instantly collapses into the opposite state. This isn't communication. It's like they're still part of the same entity.
So, we have these 2 incredible properties, right? Superposition and entanglement. But how do you actually control them to do something useful? How do you turn all this quantum weirdness into a real computation?
In your computer, we use logic gates, and, or, not, to flip bits from 0 to 1. Quantum computing has its own version, quantum gates. But you should think of these less like on-off switches and more like precise dials that can gently nudge the probability of a qubit or create and manipulate that spooky entanglement between them. And when you string these quantum gates together in a sequence, you create a quantum algorithm. It's like this incredibly choreographed dance that manipulates all that probability and entanglement, guiding the computer to explore a vast landscape of potential answers all at once. And that is how it finds solutions to problems that are impossible for classical computers.
So why does all this mind-bending physics really matter? What's the actual promise here? This is where theory hits reality, and honestly, the potential is staggering.
We're talking about things like simulating molecules with perfect accuracy. Now, why is that a huge deal? Because the interactions between atoms are a quantum problem. It's their native language. A classical computer has to guess and approximate, but a quantum computer can solve it directly. That could mean discovering new drugs in days, not decades. The same goes for designing revolutionary new materials from the atom up, or creating truly unbreakable, secure communication. And one of the most exciting frontiers is the collision of quantum and AI. So many of the core challenges in AI are about optimization, finding the single best solution out of countless options. Quantum machine learning could navigate those options in a completely new way, potentially unlocking levels of intelligence we can barely even conceive of today.
But let's be really clear, we are not there yet. The challenges are enormous.
Qubits are unbelievably fragile. The slightest vibration, the tiniest change in temperature, and they can lose their quantum state. That's called decoherence. Figuring out how to correct those errors without wrecking the whole calculation and then scaling that up, well, it's one of the greatest engineering challenges of our time.
I mean, these machines are absolute marvels of engineering. They need extreme cold and isolation just to protect those delicate quantum states they're trying to control. The hardware is mind-bogglingly complex, but the principle driving it all is profound. We are learning to compute with reality itself.
And in the end, that's what we have to remember. Quantum computers aren't just a faster version of what we have now. They are an entirely new kind of tool. They don't just calculate faster, they calculate differently. And that leads to the most exciting question of all. Once we have this incredible new power, what new questions about our universe will we finally be able to ask?